students, this is P. Venkateshwarlu, PhD Physics. Yesterday we have discussed about Young's modulus, and so what is the formula for Young's modulus? And today we have to discuss about determination of Young's modulus of the material of the wire. Okay, so what is the content mentioned? Determination of Young's modulus of the material of the wire, of the material of the wire. Okay, understand? Young's modulus of the material of the given wire. Okay, understand my children? Okay, we know that Young's modulus is longitudinal stress to the longitudinal strain is called Young's modulus. Okay, y is equal to longitudinal stress by longitudinal strain is called Young's modulus. Okay, understand, we know that formula also. Y is equal to stress by strain. Okay, force per unit area divided by delta L by L. Okay, rearrange this, we can get F into L by A into delta L. Okay, so MZL divided by area into delta L. Okay, so this is the formula. This is the formula mentioned. Okay, how we can find, how we can determine the Young's modulus of the material of the wire. Okay, understand? So for this case, we have to take two wires. Okay, understand? This is rigid support. Consider here two wires. Understand? Two wires. Consider two wires, A and B. Okay, A is called reference. B is called experimental wire. Okay, understand? See, and we can attach here fixed load, and here we can have scale, and here we can have vernier scale also. Okay, so in this side we can say pointer. Okay, see here we can apply slotted weights. Slotted weights means we can increase the weight, means by adding the slotted weights we can increase the load. Okay, understand my children? Yes. So this is slotted weights. So see here, coming to the construction, consider rigid support, consider two wires, A and B. A is called reference wire, B is called experimental wire. Understand? And A having one scale and one vernier scale. Understand how much the wire elongated after applying load. Understand my children? So this is the experimental arrangement. Now here what happened? Whenever we are applying load, means how we can apply load? By increasing the mass of the slotted weights. Here slotted weights is there. So we can increase the mass, means what happened? The gravitational force acting means weight increases. Okay, understand? So if mass is applied on the experimental wire, so we can apply indirectly load. Okay, if the mass is increases means weight also increases. If weight increases means load increases. Due to the load, wire B elongation take place. Understand? Wire B elongation take place. Understand? So by using this scale, and here vernier scale, So by using this vernier scale and we are applying load, we have to get how much length is elongated. Understand? So initially length is initial length is L. Okay, understand? Increased length delta L. Okay, understand? Delta L. Understand? Now weight means load W is equal to mg. Okay, F is equal to mg, that is equal to W weight. Understand? So then radius of the wire R. Okay, understand? By using this we have to find Young's modulus. Understand? So what is the Young's modulus? Y is equal to longitudinal stress to the longitudinal strain. What is the longitudinal stress? Force acting per unit area. Force acting per unit area divided by longitudinal strain. Delta L by L. Understand? Rearrange this F divided by A, L into delta L. Okay, understand? So then we have to take F is equal to mg. F is equal to mg. Next L divided by area. Okay, see here F is equal to mg and area is equal to. So what is the area of cross section? Pi r square. Understand? Area of cross section. So that is pi r square. Understand? Area means pi r square into delta L. So finally y is equal to mg L divided by pi r square L is the Young's modulus of the given wire. My children. So what is the experiment? This is determination of the Young's modulus of the material of the given wire. So first of all we have to take two wires, two same length and same diameter of the wire. Okay, so A and B. A is called reference wire, B is called experimental wire, in which we have to find increased length by applying load. Okay, so here we can attach load. For A is fixed, for B is variable, means by increasing weight we can increase we need to increase the length of the B because of to find the elongation. So due to this process some length increases in experimental wire. Okay, by observing this scale and vernier scale we have to find that increased length is delta L. By using this data, initial length L, increased length delta L, load F is equal to mg, that is equal to weight, radius is equal to r, area pi r square, and by using this data, by applying formula Young's modulus longitudinal stress to the longitudinal strain, by using that formula we have to find the Young's modulus of the material of the wire, my children. Understand? Material of the wire, my children. We can see here from the graph. So we can draw the graph between load and extension. We can draw the graph between load and extension. This is load, this is extension. Delta L value, this is mg value. Okay, so by increasing load, the change in length also increases. Okay, like this, we have to get like this. So here we can take a slope. This is delta L, this is mg. Okay, understand? Slope means what? Delta L by mg. y-axis by x-axis. Understand? Y-axis by x-axis. Understand, my children? By using this data, we have to change that formula. So by using this graph, y is equal to mg L by pi r square delta L. Here the value is delta L. Okay, understand? Understand, my children? So rearrange this L by pi r square mg by delta L. mg by delta L. This mg by delta L value we have to take L by pi r square into 1 by slope. Understand? So reverse, we have to take reverse. So this slope, what is slope? Slope of the load and the extension graph. Okay, understand? This is another formula. Okay, from the graph also we have to find this Young's modulus. So this is formula based on the extension. This is the Young's modulus from the graph, my children. Understand, my children? Okay, so simply you have to take two wires. One is fixed, another one is increasing weight. Due to that, the weight increased in the wire 2, it caused the extension of length in B or the experimental wire. So by finding that the experimental length, wire length and radius, we have to find Young's modulus based on the formula. Okay, by using graph also, we have to find that Young's modulus of the material of the given wire, my children. Consider reference wire and experimental wire. We can add masses and we can have length of the material is L, area of cross section A, length is L. By arranging meter scale, we have to measure the increased length in B. So and also we can arrange vernier scale to measure the increased length accurately. So by increasing mass, the length will increases. Okay, see here, length will increases. The change in length, it is denoted delta L. So we have to substitute in the formula delta L. Okay, next we have to take that extra mass. 3 is there, we have to take 2. So for experimental wire, so that is reference wire. Reference wire length increases, that length it is denoted delta L due to extra masses. Due to this extra masses, so here in reference wire the mass is constant. By increasing this mass, we have to measure the extra mass and we have to measure the change in length, that is denoted delta L by using vernier scale. Okay, here we have to find the extra load is equal to mg, that is equal to F. Extra mass into acceleration due to gravity, it is denoted F. So y is equal to, instead of F, that is equal to mg, y is equal to mgl by A into delta L. A is area of cross section, L is initial length, delta L is increased length after applied extra load. So y is Young's modulus. In this way we have to find Young's modulus of the material of the wire. So by using the scales we have to find the increased length, and by using mass we have to find that y value. Okay, my children? Yes. Bulk modulus, it is denoted B. So bulk modulus, it is denoted B, which is defined as bulk stress to the bulk strain, or volume stress to the volume strain. volume stress to the volume strain. Means volume stress means normal force per unit area. Normal force per unit area. Understand? So then volume strain means change in length by original length. Change in length by, change in volume by original volume. Change in volume V by original volume V. Delta V. Understand? See, initially we can take one object, we are applying force, normal force. Okay, after that we have to observe the volume will decreases. Understand? Understand, my children? Yes, you can get like this. Okay, this is V minus delta V. Okay, volume decreases. Okay, volume decreases. Understand? Understand? That's why you have to take negative sign. Negative. Understand? So rearrange this force per unit area F by A into V by delta V. Okay, understand? So Fv by delta V into A. Okay, understand? Understand, madam? So negative indicates volume decreasing. Negative indicates volume decreasing. By rearranging this formula, minus PV by delta V. Okay, understand? So here P is equal to force per unit area. Force per unit area. Understand? Finally, it is visible? Yes. Finally, so bulk modulus B is equal to minus PV by delta V. Okay, minus pressure into volume divided by change in volume. So what is bulk modulus, my children? Bulk modulus, it is denoted B. So bulk modulus, which is defined as so volume stress to the volume strain. Volume stress means the force is applying unit surface area of the whole body. Okay, understand? This is applied, we can say, normal force per unit area. So then volume strain, change in volume by original volume. So by rearranging this, we can get like this. So here what happens? The volume decreases. That's why you have to take negative sign. So minus Fe by delta V into A. So force per unit area, it is called pressure. Minus PV by delta V. Okay, understand? B is equal to minus PV by delta V, madam children. Understand? Understand, madam children? Bulk modulus, it is denoted B. Finally, we can get the expression B is equal to minus PV by delta V. Minus PV by delta V. Okay. So next, what? Compressibility. Compressibility, madam children. Compressibility. Okay. Compressibility. Okay. Okay, my children. Coming to next one, compressibility. So compressibility means reciprocal of bulk modulus. Reciprocal of bulk modulus. What, my children? Reciprocal of bulk modulus is the compressibility. Compressibility, it is denoted K. K is equal to 1 by bulk modulus. 1 by bulk modulus means say it is reciprocal delta V by P into V. P into V means, so here this is the formula. Coming to SI units, say 1 by Newton meter power minus 2, because pressure means Newton per meter square, that will give Newton meter power minus 2. Okay, so rearrange this Newton inverse meter square, Newton inverse meter square medicine. Understand? Newton inverse meter power minus 2 because pressure Newton per meter square, it is reverse. So these are all take in reverse means we can get Newton power minus 1 m power 2. Then dimension formula medicine. Yes, dimension formula for pressure m power 1 L power minus 1 T power minus 2. Okay, for compressibility reciprocal. Okay, so m power minus 1 L power plus 1 T power 2. Okay, understand my children? This is the dimension formula of compressibility. Compressibility, it is denoted what? K. Understand? It is denoted letter K, which is defined as reciprocal of bulk modulus. What, my children? Reciprocal of bulk modulus. Understand? Yes. So after that we have to discuss about the particular one. So applications of factors affecting elasticity of materials. What, my children? Factors affecting elasticity of materials. Okay, so my children, what is the next content? Factors affecting elastic materials. First one, hammering and rolling. Hammering and rolling. So hammering and rolling means consider a heavy crystal. So say it is body. Consider a heavy crystal or body. So by hammering and by rolling, so here large crystal is become a small crystal. Okay, like heavy body, it becomes which is divided into small particles, small crystal size. In this case, what happened? The nature of elasticity of material increases. The nature of elasticity of the material increasing. Understand? So what is hammering and rolling? By hammering and by rolling, so we can cut the big crystal into small pieces. Okay, in this process, what happens? Heavy body becomes a lighter body. So due to this process, the material which having elastic nature, the value of elastic nature increases. Next one, annealing. Annealing is the process in which the small crystal which becomes big crystal, means small particles which are made up to heavy particle or big crystal or big particle. So due to this, what happened? Elasticity, the nature of the elasticity here increases. Here the nature of the elasticity value decreases. Next, third one, impurities. Okay, see here, impurities means we can add some values. We can add some different materials are used in original materials. Like we can add copper to the gold. Understand that we can say, so adding impurity to the original materials. Okay, by adding this, by adding impurities, by adding suitable impurities to the elastic nature. By adding these impurities to the original materials, elasticity may increases or decreases. Elasticity may, which is increases or decreases. Understand, my children? And the last one, temperature, my children. Temperature. Understand? So then, fourth one, temperature. Okay, see here, whenever we have to apply temperature, whenever we have to apply to the temperature for suitable materials, what happens, my children? The elastic value increases, the elasticity, the property of elasticity value decreases by increasing the temperature. Understand? Temperature increases, then elastic nature it will decreases. But in the case of inward, okay, understand? Inward steel. Okay, so this material will not decrease the elasticity. So this is constant. So this is alloy. So inward steel is the alloy. Okay. So by increasing or decreasing temperature for this type of inward steel, which is belongs to alloys, it will not increases or it will not decreases the elastic nature. Understand? Understand, my children? See here, what are the factors affecting elasticity of the material? First one, hammering and rolling. So hammering and rolling, this process, large crystal is becoming small pieces of crystal. Due to this, the elastic nature of the material increases. Next, annealing. So annealing means the small crystal grains, it will becomes big crystal. Due to this process, the elastic nature will decreases. Then impurities. By adding impurities to the pure materials, it's may the elastic nature it's may increases or it's may decreases. And fourth one, temperature, my children. So if temperature of the material increases, the nature of the elastic property will decreases, except this inward steel. Inward steel is the alloy, means you know that alloy. So it is the combination of two or more materials, two or more metals. So it is constant, and it means the value of this elastic nature is constant with the application of applied temperature or applied cooling. Understand, my children?